So we will now discuss memory models and finally cap our discussion with data races. So we'll find that data races and memory models in a certain sense are quite intimately connected, and this will be explored in this lecture. So first let us do a quick recap of what is it that we learned. So the memory model or the memory consistency model is essentially a specification of what kind of executions are allowed, and for a piece of code what are the valid outcomes. So it basically determines the rules, and the memory model is dependent on the processor architecture, even though as we shall see we can also define memory models for virtual machines, for software, for compilers and so on. But the way that we have been explaining up till now, it has primarily been defined in the context of a processor architecture. So we can have very aggressive optimizations, so then the memory model becomes rather weak. And so the gold standard or the strongest memory model is sequential consistency. So PLSC requires the WS and FR orders to be global. So this was a direct consequence of PLSC. And all popular architectures follow PLSC, and they implement coherence, which ensures PLSC. And many also disallow thin air reads, which as we saw can happen if we have value prediction, along with a couple of more pipeline optimizations. So the only orders that we can actually change, right, which are not global, which are local, are RF and PO primarily, right? So RF, well, as we saw, we can have two RFI and RFE. RFI is read your own write early, and RFE is read others write early. So reading others write early is same as non-atomic writes, and all kinds of program order relationships can be relaxed. That is what we saw. Relaxed means not followed. So let us now look at a series of execution witnesses, and let us see how observing something and not observing something, how it actually allows or disallows an outcome. So we will discuss a couple of execution witnesses here, but my advice to the readers and viewers would be to look at this in detail in the book and actually go through these examples in great detail. So let us first look at the order which is relaxed almost all the time, the write to read order. And this is a direct consequence of having an out of order pipeline, load store queues, forwarding, write buffers and so on, where essentially if there is a write and then a read comes after that, well, the write of course executes at the end at commit time, but the read executes earlier. So the read in a sense is visible to other processors earlier than a write. So this is a direct consequence of out of order processing as well as other kinds of optimizations, right? So typically many architectural structures can kind of relax an order. So let's look at one example and let's try to study it. So we first set x is equal to 1, then there is a read instruction after this. So the read instruction in a sense reads it early, but let's assume it does not do that, right? So we will see what will happen, right, if it does and if it does not do that. So let's just look at these three instructions A, B and C, where we write 1 to x, we read 1 from x, right, because this anyway we will have to read because it's the same thread, and then we write 1 to y. So till this point it is fine. After that what happens is that instruction D reads 1 from y, which is also fine, and then we have two read operations. So let's assume the program order between them holds. So then what are we going to read? So well, we have two options, either we can read 0 or we can read 1. So if you see the outcomes, we have read t1 equal to x is equal to 1, t2 is equal to 1, right? So now the question is, what do we read t3 to be? So in a lot of architectures, what you will practically see is that the core will read its own write early before the write is actually visible to other cores. Other cores or other threads, it means the same thing in the context of our current discussion. So what T2 will actually do is when it tries to go and read the value of variable x, it will get an older value which is 0. And needless to say, then the FR, the from read order will hold between Rx0 and Wx1. So if the RFI, so let's see out of this, what is it we can relax. So if we have atomic writes, we can't relax this. If we observe the read to write order, we cannot relax. And most of the time we do. And read to read also, if we observe, we cannot relax. And FR is global anyway. So this execution will not be valid because there is a cycle if the RFI order is global, but most often it is not. Most of the time it is not when we are using an out of order pipeline. That is why this edge will not be there. Hence, in any architecture where the RFI order is not global, but the rest of the edges are global, this execution will be allowed. All right. So this, in a certain sense, is a fair execution because we should be allowed to read our own writes early. So this LSQ forwarding will give us this, write buffers will give us this, and then the write later on can be visible to the rest of the other cores. So this is a classic out of order pipeline optimization where we finish the loads early, primarily because loads are on the critical path and we would like to finish them early. So that's a vital feature for a speed up. So that's why this execution will by and large be acceptable in almost all architectures with any semblance of out of order execution. So this is kind of the implication of the RFI order being global, right? So now let us look at the RFE order. So here, of course, we look at non-atomic writes. So we have already seen something of this nature earlier also when we introduced the idea of non-atomic writes. So here what we do is that, so as we were discussing, non-atomic writes can uh, come about in an architecture if we have a local tile of, let's say, caches. In the sense, we divide our entire chip into tiles of core cache bank complexes. So it is possible for another core in the same tile to read the write of the sister core before other cores have seen it. So this can happen particularly if they share a Snoopy bus between them, and so this is definitely a possibility of reading others' writes early. And also what can happen is if they share some other structure like an MSHR or something, then also this can happen that before others have seen it, one core will see the write and then take decisions on the basis of it. So let's do a quick recap of the execution that we had seen earlier. We set x equal to 1, then we read the value of x, we read it to be 1. Then we set the value of y to 1, we read the value of y to be 1. We assume program order over here. And then we read the value of x. So if this write would have been atomic, we would have read 1, as you can see clearly from this sequence, but we actually read 0. Consequently, there is a cycle in the execution witness because we need to add an FR edge between Rx0 and Wx1. And needless to say, if the write would have been atomic, this behavior would not have been allowed. But given that writes are not atomic, we will not have this edge. If you don't have this edge, you see that there is no cycle and this execution is allowed. So basically what we are doing is that we are essentially seeing writes to different locations in different orders. So T2 sees x, so x is written to x is written x is set to 1 first and then y is set to 1, whereas T3 sees that y is set to 1 first and then x is set to 1. So we are essentially seeing writes to different locations in different orders, which is a hallmark property of non-atomic writes. But even in with non-atomic writes, we still have PLSC, so we see the writes to the same location in the same order. But for different locations, that is where there is a little bit of mix-up. Primarily because this edge is not global. That's the main reason. And that is why we do not have a cycle in this graph. Alright, so let us now look at the next edge, which is typically relaxed, which is the write to write order. So this can happen in a non-blocking cache, where what will happen is that the first write will kind of get stuck in the MSHR, but the second write for many reasons, the second write we might either directly affect the write, or we might send it to the lower level bypassing the MSHR. For a wide variety of reasons, the first write might get stuck, might get delayed, but the second write might reach the rest of the course. So we will see that even for the same thread, as long as the addresses are different, the write to write order is being violated. And typically in non-blocking caches, where we would stop a write at an MSHR and we might let the other write go through, that is where such problems can happen. So here also a simple example would be we write 1 to x and 1 to y. So we have wx1 and wy1. We add a program order edge between them, which is exactly what we are contesting. Let's assume we have atomic writes. So then we read ry1. Then let's assume we have a read to read order. So this is not something that is being contested. And then we read x to be 0. Right? So that is so that's essentially the crux, that we read y to be 1. In the world of the atomic writes with write to write order, we would have read x to be 1, but we read x to be 0. That is why we need to add an FR edge between Rx0 and Wx1, and we have a cycle, so this execution is not possible. But if the write to write ordering would not have held, then what would have happened is we would not have added this edge. Then there would have been no cycle and this order would have held, right? So this execution would have been fine. So what again is the summary of our discussion? That T1 will see the write to x first and the write to y later. T2 will actually see them in the reverse order. It will see the write to y first and the write to x later, right? So here also we see write to different locations in different orders, and this is perfectly fine if we write our code in this manner and our write to write ordering is not respected. This is exactly what we are going to see. All right. So that is why when multiple addresses are concerned, unless we add fences, others will not be able to see the data. And this does have a lot of implications when you are writing, for example, communicating values. So what we might do is we might set, so let's consider two threads, right, T1 and T2. We might set result is equal to, let's say, some value, let's say whatever, 57. Set status is equal to 1, which indicates that the computation is done. Then we read the status, right? If status is equal to 1, which is exactly what we are doing over here. And then we read the result, right? So we set some temporary is equal to result, but we are not guaranteed to see this result. The reason we are not guaranteed is that these writes might get flipped, right? So because this ordering is not guaranteed, this kind of a code pattern will not work. It is not sequential consistency. So we need to add a fence over here. If we add a fence over here, then of course we are guaranteed to see the correct behavior. Alright, so the next tricky one is the read to read order. And this is very easy to violate because, well, we are talking of two different reads to two different addresses. And this ordering is always relaxed in an out of order processor with an LSQ, where we might have two reads, and then they are simply issued in different orders, right? As simple as that. That one read is stuck for some reason. So let's say we have an LSQ and we have some sort of a predictor, right, of whether we'll have a dependence or not. So we have two reads, read to X and read to Y. So the read to X, we predict that there will be a collision, so it is kind of stuck. So we do not let it read any data and we don't send it to the cache. But the read to Y, we predict there will be no collision, so we send it to the cache. So in a certain sense, violating this read to read order with aggressive optimizations, particularly a load store queue where we employ dependence prediction, is actually very easy. And we have seen that happening in chapter 5, where the read to read order got violated pretty easily. So in that case, what we need to do, let's consider this example first where we read X and Y. And so let's say we read X to be 1, we read Y to be 0. So from Rx1 to Ry0. Then we set Y to 1, so we add an FRH. Then we read Y to 1, so we add an RFH. And then we have a program order edge over here. So the program order edge is between R and W, a read and a subsequent write. And WX1 then provides the data to RX1. So in this case, if the read to read ordering is relaxed, what will essentially happen is that we will essentially reorder the reads, and that will cause us some trouble, right? So the read to Y, if it goes earlier, it will read an early value of Y, which is 0. And then of course X will return 1, and as you can see, there will be a cycle in this graph. And any kind of a processor with an aggressive out of order load execution scheme, with of course an LSQ where we are not bound to issue loads in the order in which they were fetched, and this can happen, particularly when we predict dependencies and so on. This will happen. This is definitely a possibility. This will happen, and if this happens, then this execution will actually have a valid outcome. So now we can have two kinds of processors. So Intel processors, for example, enforce a read to read order. In this case, this execution is not allowed. This outcome is not allowed. But in most other out of order processors, this execution, this edge is not there. If this edge is not there, you can easily see that this outcome will be allowed. Now let's come to a read to write order. So a read to write order is pretty hard to violate actually. So what does this mean? This means that there is a read and there is a write. To violate this order, what will happen is that we need to execute this read after this write. So we need to execute kind of this read over here. But that is not really the way that this will actually happen. Because just look at when the write will execute. The write will execute when it reaches the head of the ROB. And by that time, the read would be gone. And so read will not be in the pipeline, so it must have finished its action, it must have gotten its value, and it must have gone. Alright? And so there is simply no way that we will actually, in a sense, overtake it. But it is possible in several scenarios, right? So one of the scenarios in which it is possible is if, let's say, we have a speculative write, in the sense that we have an aggressive optimization where we actually do a write before an instruction reaches the end of the pipeline, right? So we kind of do an aggressive write. Another example could be where, let's say, these are two separate hardware threads and they share the same load store queue that actually stores physical addresses. In this case, writes can be visible early, right? So they can be kind of speculatively visible. So in that case, you will have such outcomes where, let's say, we read first. So essentially, the our problem is with the outcome T1 is equal to 1, T2 is equal to 1. That is because in both the cases, the right instructions, the right operations are the later operations. So both the reads cannot be 1. Otherwise, we'll have two program order edges, right, over here. Two RF edges, which we presume to be global because writes are atomic, and we have a cycle, right? So in a lot of processors where the read to write ordering will hold, in a lot of simple processors, you will not see this execution actually, because in them the read to write ordering will hold. But this will be visible in many aggressive implementations where the write is visible early because of some of the reasons that I mentioned. In that case, this outcome will be allowed because we will not have these edges. So there will be no cycle in the execution witness. All right. So given that in this case, this order will not hold, we will find this outcome to be legal. But as I said, this is the most difficult order to violate because this flies in the face of whatever we have been teaching in the out of order pipelines. So unless we have extremely aggressive optimizations, it's rather unlikely that this order will get violated. So let us now look at an important corner case. So the corner case is like this, that we have up till now been maintaining that in sequential consistency, all the relations are global, right? But now I would like to ask a simple question that let's say we relax the RFI relation and everything else is global, which means that a core can read its own write early. Will it break SC? Well, the answer is no. So this relation can be relaxed in SC and the proof is there in the book. So the broad contours of the proof are like this, that let's say we have a write and then we have a read, right? So the read reads the value from the write. Then another core sees the effect of the read, of course via other instructions, could be in the same thread as well. And then it does a couple of other things. And finally, there is a cycle that goes back to the write. So this is how a cycle would form, and then you would say that, look, this execution is not an SC, right? But what I am saying is that, and this is something that is been argued in the book, that this will actually not happen. All right. The reason it will actually not happen is because there will be an ordering between, let's say, this instruction and instruction in the other thread and the write, right? Because either the dependency will go via this read. In this case, the only dependency from a read to another will be to the same address, a read to a write. So you will have one edge like this. So we'll not have a cycle. Or it will go via other instructions. In all cases, it is possible to prove that we will actually not have a cycle. This is an important aspect of sequential consistency, that it does allow the RFI relation to be relaxed. The primary reason being that other cores will not be able to make out that it actually has been relaxed because they will not see the effect. So the execution will be indistinguishable from a situation where it is not relaxed, and other cores, for them to see, they will either see it via other instructions or via the read instruction. But then again, the write instruction will have to execute before them. There will be happens before relationship between the write and those instructions, those other instructions. And that is why we will actually not see the effect. But I don't want to go very deep into it. The proof is there in the book. But this should be kept in mind because we'll use it in this next figure. So this actually shows a summary of memory modules. So sequential consistency is at the very top, where as you can see nothing is relaxed. It has atomic writes. This is for atomic writes. And we have relaxed the RFI relation in sequential consistency because we just showed in the previous slide that it's possible to do so and get away with it. Then we come to Intel's memory model, which is a total store order memory model. In the sense, the only two relationships that are relaxed is the write to read order. This of course has to be relaxed because we are dealing with an out of order pipeline, and we also relax the RFI relationship, which incidentally all models here do, primarily because without that the benefits of an out of order pipeline are not going to be there. Next, we have processor consistency, which is also quite popular in distributed systems, because a memory model is not just limited to a processor architecture. We can extend it to a distributed system or a programming model. So the additional advantage over here, the additional relaxation over here is that writes are not atomic. So in processor consistency, it's the same as TSO. The write to read order everybody is violating, but the writes are, in addition, the writes are not atomic. But the important thing is that write to write orders are maintained. So one processor, even with non-atomic writes, it maintains its own write to write order, and that is where the term processor consistency comes from. Then we have PSO. So PSO is kind of similar to what we call PC, processor consistency. It is just that it has atomic writes, but it does not obey the write to write ordering. Okay, so that's the swap over here. That internal within the thread write to write ordering is not respected, mainly because we'll have non-blocking caches and so on. And but writes are nevertheless atomic. Then we have weak ordering and release consistency. So what's the difference? So weak ordering, we don't respect anything, which means we do not respect any of the orders, but we still have atomic writes. And in this case, we have a fence, we have a generic fence instruction. But as we have seen in release consistency, we have a pair of fence instructions. We have a release and an acquire. Sorry, it should be in the other order. It should be an acquire and then a release. So the idea of acquire and release is that we will have it's like an acquire a lock and release a lock. So the instructions of the critical section are within it. So the reason that we need a fence, before and after a critical section, or let's say in generic terms an acquire. So the idea of an acquire is that first I acquire the lock and then I execute the instructions of the critical section, or in other words, no instruction of the critical section can execute before the lock has been acquired, or let's say this particular instruction has executed, right? The acquire instruction is executed. So that is the idea. Release basically means that what we do is that we can, after executing the release instruction, it means that all the instructions in the critical section, including the acquire, have finished. So release signals to the outside world that look, all the instructions of the critical section have finished, so you can go and read their data. Unlike a traditional fence, it does not prohibit instructions after it from completing before it. So that much of out of orderness it allows as compared to a regular fence. But acquire and release essentially limit the behavior of the critical section that lies within them. So even release consistency does not obey any of these program orders. It nevertheless has atomic writes. And no memory model actually respects RFI. The IBM and ARM models are outliers in this sense. In the sense they don't respect anything. So they have non-atomic writes. And additionally, they also do not respect any of the program orders, right? So none of the POs they respect. But they do have fences though. So the reason we can write correct code in the IBM and ARM memory models is because they have elaborate support for fences. And not just regular fences, but all kinds of fences. Fences between stores, between loads and so on, which allows us to write fairly efficient code. So who needs to know about memory models? Well, the answer is pretty much everybody who works with multi-threaded code. Otherwise, they will make mistakes because they will assume that the system operates in a certain way, but it will actually not operate in that way. mainly because internally the processor can reorder instructions and you will see different outcomes. Furthermore, what can happen is that maybe a certain piece of code which is actually buggy will work correctly on a certain machine, but on another day it might not work correctly, right? So we might have this parallel code which on one day works fine, but on the other day produces a non-intuitive outcome which the programmer will not be able to explain. So most library writers and people who deal with low-level code, right? So library writers, OS writers, compiler writers, all lot of people who deal with low-level code, they need to understand the intricacies of the memory model in great detail because the main aim is to minimize the number of fences. So minimizing the number of fences as such is an undecidable problem and it is actually very hard to solve. But there are variants of it. There are tools that can suggest where to avoid a fence and so on. So clearly minimizing the number of fences is a research problem in its own right, and there are many tools to help us minimize them. But also black belt programmers know where to have a fence and where not to have a fence because they understand the memory model in great detail. Alright, so now the question is that we have used the word a black belt programmer. What that means is it is a programmer who needs to understand the memory model in great detail to actually write correct parallel code. But the question is that do we expect most programmers to be at the black belt level? The answer is no. So we need to design something far simpler for the average programmer such that he or she can write correct code which will run regardless of the memory model and which will also run on all machines regardless of their memory models. So what is the solution? So let us go back to the drawing board and say that look, the memory model is great, I totally understand it. Coherence is great, I totally understand it. And I totally understand SC, RC, PC and everything else you have thrown at me. But at the end of the day, I don't care. I want to write a piece of parallel code which will run on all machines regardless of their memory model. It will just simply run and it should be simple to program. And I don't want to learn a memory model and I'm not interested. Alright, so and I'm not a black belt programmer, I don't care that much about performance. So I'm willing to tolerate a little bit of slowdown. You kindly give me something which is slow but reduces my headache and runs everywhere. So basically performance for me is not that big of a concern. So I'm okay if it is slow, right? I'm okay if it has a lot of fences, but I just need simplicity and portability, right? It has to be simple and it has to be portable in the sense I write it on an ARM machine. The same code should run on an Intel machine and vice versa. Okay, so let us look at the same logic or same code, counter plus plus. So if I were to break it down into 3 assembly statements, and I'm just writing it in the C analog of assembly, I'm not writing the assembly. I will read counter, put it into a register, increment the register, and then write the register back to the counter variable, right? So this is how a RISC ISA would do it by breaking into 3 instructions. And if I cannot run multiple copies of this code in parallel because the output will be wrong, and we have already seen this. So what I can do is I can use an atomic instruction like fetch and increment. So this is guaranteed to work. It will take counter, replace it with counter plus plus, and the entire thing appears to happen instantaneously. So this is atomic, right? So I have no problem at all. Instead of using that heavy piece of code, I'll just use this. I could do this because this is simple. But if I had a piece of large elaborate logic, I actually could not have done this. Then you would have argued that I need to have lock and an unlock mechanism to ensure that this piece of code executes correctly, which is something that I will show in the next slide. So if we do not want to write code using atomic instructions, because in many cases, we'll not be able to do. The logic might be very complicated. We can encapsulate them in what is called a critical section, which will begin with a lock. We have seen how it works. Which will end with an unlock. We have seen how that works. And then we will just execute. We'll have a lock and an unlock, and the code in between is called a critical section, and every lock has a lock variable associated with it. So as long as we lock the lock variable, nobody else can get in. And furthermore, if any other place counter is being used in some other context, if that is also locked with the same variable, then that will also ensure that nobody can get in and update the value of counter and cause an error basically. So what are we doing? So what we are doing for this critical section is, if we have two threads T1 and T2, T1 locks, T2 tries to acquire the lock, it is not able to acquire. T1 does an unlock. So T2 keeps spinning as we have seen. Then T2 gets the lock. It executes for some time. And finally T2 releases. Alright, so this is the typical way that we work, where one thread acquires the lock, executes a critical section, other threads keep spinning. Once a thread relinquishes the lock, some other thread gets it. It gets exclusive control of the critical section, executes it, again unlocks, so on and so forth. So now the question is, why do we need to use locks? Well, so let's start with two philosophical questions. So assume that we have a large piece of multi-threaded code, but there are no shared variables. If there are no shared variables, do we still need to use locks? The answer is no. The reason is that if there are no shared variables, so we will not have the kind of concurrency bugs that we have actually seen. So why were the concurrency bugs happening? They were happening because we wanted this piece of code to execute atomically, but it was not. So let's say we will read, two threads will read counter to be 100. Then they will set it to be 101. But 101 should not be the final state. The final state should be 102. So this is happening only because the counter variable is shared. If it was not shared, there would have been no issue. So this is number one. If there are no shared variables, we don't need to use locks. So when do we need locks then? We need locks when two blocks of code make conflicting and concurrent accesses to the same address. The same address is the same variable. So what are conflicting accesses? They are a pair of accesses where at least one of them is a write. Because if there are two read operations, we don't really care, in which order they are happening, and they will not cause any correctness issues. So we don't really need to care. The problem comes when one of them is a write. So you go back. The problem is only coming because we are updating the state of counter. If we didn't update the state of the counter, there would have been no issue in just reading the value of the counter. We didn't need a lock and unlock function. The problem is coming because we are updating the value of the counter variable, and that is where we need this mutual exclusivity of the critical section, right? So basically the codes of course have to access the same address and make conflicting accesses, which means at least one of them is a write. If both are a read, there is no problem at all. One of them is a write, like it's like this, or both of them are writes. So in that case, it's a clearly conflicting access because the final state is dependent on their order. And also, it's a large block of code, so we might have many reads and writes. The entire thing will not be correct unless we have a critical section. What is concurrent? Concurrent means at the same time. So you go back and let's look at informally. Informally, what concurrent meant over here is that two threads execute at the same time, both read counter at the same time, in the sense they read both the values to be 100. Then ultimately they just write 101. Since there is an overlap in their execution, they in a certain sense are concurrent, informally defined, and that causes all the trouble. So the common sense meaning is at the same time, but I think we can do better. So let's look at the code for incrementing the counter. So let's say that we read the counter to be 0, read it to be 0, and we update it to 1. So what are we doing? Rx0 to Wx1, let's add a program order edge. And Rx0 to Wx1, so this is the execution witness over here. We again add a program order edge. Okay. And then what you see is that we have two FR edges like this. And we have a write serialization edge because let's say this write happened after this write. So this is pretty much the execution witness that you see over here. And this does not really convey a lot of information. And all that it tells us is that, look, the execution witness is fine. But in spite of that, the behavior is not satisfying us, right? So there are no cycles in execution witness as you see. And also the execution witness, if you actually see, it is sequentially consistent. In a sense, we can order the operations like this. So it is an SC, but even if it is an SC, we are still not happy because we don't want the final value of x to be 1, we want it to be 2. So clearly we need some tool or some additional rider on the execution witness to actually make it more expressive such that this particular case of this concurrent conflicting access, right, this can be taken care of. So let us now look at a slightly different kind of program, and this might give us an insight. Here we want to transfer the value of a variable from thread T1 to thread T2. So what we do is we set x is equal to 1 and then we set, so let x equal to 1 be the result of our computation. Then we set y equal to 1 and then we read the value of y. So as long as y is not equal to 1, we just keep looping, and when it is 1, we come down and then we read the value of x. So if we have atomic writes, then what will we actually see? So what we will actually see is that we will see the value of this to be Rx1, but of course we need a few program orders to hold as well, and only then we are going to see. But there is also an important point that I would like to mention here. Assume that y is a sync variable in the sense that y over here is updated only using atomic instructions, the kind that we have seen before. So in this case, what you will actually see is that we will write 1 to x. There will be a program order edge to wy1, right? So let us for the time being say that this is for an arbitrary memory model. I don't really care. So then what we will see is, because y is a sync operation, in all memory models you will have the wx1 to wy1 edge. Then you will also have a synchronization edge, an SO edge, this being the most important, between wy1 and ry1, because we are reading, so recall that all the synchronization operations between them are sequentially consistent. So we will have an SO edge between them, and then we will have a program order edge between ry1 and rx1. And given that there is a synchronization edge, so wy1 would have expected, there is a fence also inside it, the wx1 would have completed. So regardless of whether RF is global or not, we are guaranteed to read Rx1 at this point of time. So what we see is that in this execution witness, we are able to see some patterns. If we look hard enough, there is some pattern that guarantees that, look, regardless of the memory model, if x is set as 1 here, x will be read as 1 over here. And our exact memory model doesn't work. It is not important. And the reason is that y is a synchronization variable. So there is a strict program order edge here. There is a synchronization edge here and a strict program order edge over here. So we are guaranteed to see the effect of this, right? So what we can say is this is an execution witness, and the magic sauce is that we have two of these synchronization operations with an SO edge. So there is a path from Wx1 to Rx1 that has an SOH, which is what guarantees the correctness or guarantees our original intent. And so the SOH must be having something to do with capturing the original intent of our program. So let us now take our discussion a little bit further. So what we are trying to say is that let us say that two accesses are concurrent when there is no path between them in the execution witness that contains an SOH. So what is so great about an SOH and why are we making a big deal out of it? Well, let us look at this execution witness once again. So what an SOH is essentially capturing is, it is capturing the synchronization from the viewpoint of a programmer. So the programmer wants that before an access to this synchronizing variable y, all previous accesses are done. Then another synchronizing access is made over here, and this has to strictly be after setting y to 1, and all subsequent actions are after that. So this is what the programmer wants, and the way that the programmer is enforcing this wish of hers is basically via having these synchronization instructions and these sync edges, right? These SO edges, all right? So the important point over here is that if, let's say, between any two conflicting accesses to the same variable, we have an SO edge, it basically means that the programmer's intent is being captured, that we make one access, then we pass through a synchronization and make the second conflicting access. So this means that the conflicting accesses in a sense are controlled, and controlled by whom? Controlled by the instructions inserted by the programmer, and this means that this execution is going according to the wishes of the programmer. That is, broadly speaking, an informal representation of the situation. So we are trying to slightly formalize it. So we say, let's consider an execution witness, and let's say within the execution witness, two accesses are concurrent, which essentially means that there is no synchronizing access between them. All right. So consider a write and a read to the same address. So let's say there is an RF edge between them. So we say that it is concurrent because primarily it is not passing through any programmer specified structure, right? It is not passing through any kind of a synchronizing access like a lock or unlock. So as far as we are concerned, we can have another execution where we could very well have this, right? And because it is not controlled, and let's say if other variables are dependent upon this order, they also need to reflect this order, right? And that might not happen, and this is exactly why we want all such interactions between accesses to the same variable, one of which being a write, pass through the synchronization edges, which essentially are put to capture the intention of the programmer, right? So a critical section is one example of such a synchronization edge, but it's not the only example. Here we have a critical section, we unlock, and then another thread enters the critical section, and there is an SOH. So all of the accesses over here are strictly before all of the accesses over here, and they happen before just because of the SOH, and this ensures that, let's say, for example, we are setting x to 1 and we are setting y to 1, and then here we are setting x to 2 and we are setting y to 2. So it is never the case that we observe some kind of a partial state, in the sense that for all other threads they will observe x equal to y all the time, right? And because they cannot make any other access, they cannot access x and y without acquiring the locks, and once you acquire them, you'll always see x equal to y. So this is how the synchronization edge and critical sections capture the programmer's intent. However, it is possible that while writing the program, the programmer might make a mistake and there might be a pair of conflicting and concurrent accesses to the same regular variable, right? It's a non-sync variable. There will be conflicting accesses which are also concurrent by this definition. They are said to constitute a data race, and the execution over here is actually a data race because we see concurrent conflicting accesses to this to the variable x, and there is no programmer intent anywhere, so there is no effort to synchronize them, and so that is exactly why we are not seeing we are trying to increment a counter, but the final result is wrong because the programmer has not added any synchronization, right? So what we should see is the final value should be 2, but in this case it is 1, which is not correct. That is primarily because there are no SO edges in the picture. So data races are bad things. They are essentially bugs, and they prevent the successful execution of a program. So now let us take a deeper look at data races and see what they actually mean. So here I would like to slightly specialize this definition because there are several things, and this is a very theoretically deep area. A lot of the proofs are there in the book, but I am deliberately going to gloss over them and present them in a very 20,000 foot level informal fashion, primarily because I don't want to bog you down with all the theory. So the book is there for it, and I would request all of you to read these sections pretty thoroughly, but I will explain the broad idea. So now I want to differentiate here between two concepts. One is the data race in an execution, the other is a data race in a program. They actually mean different things, but we will see that they are beautifully connected. So that is the beauty of this entire theory over here. One is, the first concept is the data race in a given execution, right? So what we do is we create an execution witness for it, and we look at all pairs of conflicting accesses to the same regular variable. If they are concurrent, we say that look, this execution witness has a data race, right? And the other is, so this is where a data race is a function of an execution, right? So for a given program, we can have a lot of execution. Some might display data races, some might not. So that is why we have a lot of data race detection tools, and sometimes some executions have data races, sometimes the executions do not have data races, as we saw in this example with we will see one example later that shows this. The other is that we will try to determine what actually is a data race free program, and there we will need some theoretical tools. So this is not very clear because the execution witness by definition has edges that belong to a certain memory model. So the data races, you will be tempted to think that they have something to do with the memory model, but actually they do not. But I would like to go slow, so I would like to introduce theorem after theorem, and I'll only explain the main result, not the proof, because as I said, this entire stuff is quite deep. Alright, so let us now try to answer some basic questions. So where are we here? We said that look, data races are a bad thing. Why are they bad? Because a conflicting concurrent access in a certain sense is not appearing to capture the programmer's intent. Because whenever parallel code is being written, right, and we have a conflicting concurrent access, it basically means that you can read, write variables in the same variable in any order. So then the final outcome is questionable, right? So that is why the programmers like to regulate any conflicting access to the same regular variable, that they will say that okay, you want to modify x, no problem, go ahead and modify, but then before doing this, do something like acquire a lock. After it, do something like release a lock. Next time you want to access, again go via this mechanism. So this will ensure that at least a set of variables, or maybe if you have read or written it, right? So a set of accesses and a set of accesses here, they internally make sense. Alright, the program on a whole makes sense. So that is why we define data races, because we thought that they are a good tool that capture the programmer's intent as far as a parallel program is concerned. Otherwise, we saw that if we had data races, even a simple counter update by multiple threads, that was turning out to be wrong. But the moment we introduced synchronization variables, it turned out to be correct, right? And so now let us take it further. So let us answer a few questions. Does sequential consistency imply data race freedom? In the sense, let's take a program and let's say that we run it on an SC machine. Will that imply that there are no data races? Well, take a look at this piece of code. So in this piece of code, we have Rx0, S1, S2 and Wx1. So this is sequentially consistent, all right. And as you can see, there is an SO edge between these two accesses. So this execution is data race free. Now let us consider one more. So we have not assigned a meaning to the synchronization accesses S1 and S2. But if let's say they happen to execute like this, where S2 Wx1, right, Rx1. So I write and then I read, all right, and then I have the second synchronization access. So here we have a data race. Why do we have a data race over here? Well, the reason we have one is because there is no synchronizing edge between this write and this read, and this to us represents a data race, which is something we wanted to avoid, right? So SC does not imply data race freedom, because as we can see, this is an SC machine, all right. This is a legal sequential execution. This is a legal sequential execution, but there are data races. So data race is something which is most likely, at least it appears at this point, something stronger than SC, all right. So we will go into what stronger and weaker means, but at least sequential consistency does not give us data race freedom. So what does? Let's see. Let's say that I have a program which is data race free. We will see what this means in slight detail in the next few slides. But let us say that all executions of the program are data race free. All of them. Does it imply that all of these executions are in SC, right? So let's say that we take a program and we just execute it without caring about the memory model. And so we will come up with a bunch of executions, right? I claim that all of these executions are in SC. So lo and behold, this actually happens to be correct. So this is a fantastic result, which I would say is arguably the most important theoretical result in all of computer architecture. Some might not agree with me, but at least as far as I am concerned, this is the most important result, important with a capital I, result in computer architecture, which says that, look, if all of your executions are data race free, then data race freedom does imply SC. And of course, I am not, all the bells and whistles I am not mentioning of what exactly are the other constraints and so on, but they are all there in the book. But we are looking at it broadly from an angle where you are not interested in the corners. Okay. So the salient point is that, look, if let's say all accesses, conflicting accesses for the same variable across threads have an SO edge between them, there is at least one path with an SO edge between them, right? There will be an SO edge in at least one path, which means they'll be ordered by a synchronization edge. Now let us do something. Let us take an execution witness, regardless of the memory model, and add all the SC edges. So what are they? So the SC edges will basically make RFE global, and all the program order edges will be global. And then let's see what happens to the execution witness. No problem. So if the execution witness is acyclic, it means that the execution is in SC. Let's assume, just for the sake of assuming, that there is a cycle. Then it is easy to prove that if there is a cycle, then there will be a cycle of sync operations as well, right? So there will be a cycle that contains sync operations with a happens before relationship between them. So if this is a sync operation, this will be happens before relationship. A global happens before relationship, S1, S2, S3, so on and so forth, and ultimately back to S1. We claim that this is not possible. This is not possible because the claim is that sync operations by themselves follow sequential consistency. And the reason that we say so is basically because sequential consistency is program order plus atomicity. Synchronization operations do follow program order because they have a fence within them. And atomicity because they are atomic operations, so they follow atomicity, that's obvious. So they follow SC, so they cannot have a cycle between them. So there we have a contradiction. So this is the broad outline of the proof. So the proof basically says that, look, do not care about the memory model. Okay, the memory model as such is not important. If you are guaranteed not to exhibit any data races, right? Even in the most, even with the most restrictive memory model, which is SC, it is guaranteed that you will not show any data races. Then this does imply that the execution will be sequentially consistent, right? All right. So what would this exactly mean? This would exactly mean that whenever there are two conflicting accesses to the same variable, you do something, in a sense you enclose them in a critical section where we have one synchronization operation at the beginning, one at the end, again one at the beginning, one at the end, such that any order between them is passing through an SOH like this. If that is the case, let us not worry about the memory model. Anytime you execute this, regardless of the underlying model, the execution will always be in SC. So this is very, very powerful. This basically says that, look, the memory model should be designed by the architects. It can be as weak as possible to enable performance. We simply need to add as many fences as is required, fences and atomic instructions with the synchronization capability as is required. We would ideally like to minimize them because they are expensive. But as long as we are avoiding data races, we are good. So we can reason about our program in terms of sequential consistency, which we wanted to do originally, right? We never liked parallel executions. We always wanted a parallel execution to be somehow equivalent to a sequential execution one after the other, but we were not able to do that with our execution witness based method because our sequential execution was not legal. But in this case, if let's say it is data race free, we can equate it to a legal sequential execution and we can reason about it. So it will become very easy to write parallel code because as human beings we love to think sequentially and we don't think in parallel. So once it's an SC, our proofs and our tools, everything start working and our reasoning becomes very, very easy and simple. All right, but this is not the only theorem. So where are we? SC does not imply data race freedom, but data race freedom implies SC. Okay. What else? So this is one. The other is that let's say I have a data race. What would that imply? Right? So we are now in the previous slide, we looked at the question that if I don't have a data race, what happens? If you don't have a data race, well, that is great. You are sequentially consistent. But now the question is, if I have a data race, then what? If I have a data race, then there is another theorem, which is again a beautiful theorem, and I would also rate this very highly in our computer architecture world, because typically, unlike the mathematical sciences, we don't have a lot of theorems in computer architecture, right? And the number of theorems that we have are far and few, but a few that we have are reasonably powerful. So this is one. This is the second one. So it says that, look, if you have a data race in a program, you can construct an SC execution that will also exhibit a data race, right? Which means that under any memory model, if let's say you have a data race, in the sense it is possible to have two accesses, conflicting accesses to the same variable without an SOH between them, you can then create an SC execution that will also have a data race. So proof, again, refer to the book. This is kind of an involved proof, but what does it actually imply, right? So this implies something significant. It implies, so let me write it down. Data race in a program implies that SC exec with a data race. So I can kind of flip this around and consider the contrapositive. That let's take a program and let us consider all of its sequentially consistent executions. If let's say there are a billion of them, we can't do it manually, but an automated tool can. So it can construct all of these sequentially consistent executions. If none of them exhibit a data race, we can say that the program does not have a data race. Okay, so this is very important. I don't mind repeating this 20 times because this is capturing a large part of our argument. So hear this again. So what do we know? That we say that look, under some memory model, if you are seeing a data race, you can always construct an SC execution with a data race. Consider the contrapositive of this. So in contrapositive, what we do is that we reverse the sign of the implication, and then what we do is that we say that if, so this stands for the not, right? See, if there is no SC execution with a data race, it implies that the program does not have a data race. Alright, so in this case, data race becomes the property of a program, and what it basically implies, or what it basically tells us, is that if an automated tool cannot construct an SC execution with a data race, then the automated tool can always see billions of executions and see if those executions have data races or not, but assume that it cannot construct an SC execution with a data race. Then it means that the program is data race free. In other words, we are defining a data race as also a property of a program, and it basically says that look, consider all of its executions, notably its SC executions. If there is no data race, then the program itself is data race free. So what you should do is that you should write programs that are data race free. They will run on all memory models, and that too in a sequentially consistent manner, right? So basically the point is the underlying architecture is free to determine its memory model. You write your program, don't care about the memory model, and then just ensure it is data race free. Run it on the architecture, it will run. But what happens is sometimes when we write large programs, we can make bugs. We can have bugs, we can make mistakes. These will be concurrency bugs. Notably, we will have a data race. When we have a data race, it is possible that maybe in 100 executions we don't see a problem. But in the 101st execution or the 1001st execution, we might notice a problem. That is where we need an automated tool, and there are many such tools available, which will basically sequentially enumerate all the sequentially consistent executions, search them for data races, and finally verify that a given piece of code is data race free. Alright, so we'll also look at other approaches, other kind of semi-formal approaches later on, but the basic idea is that it is possible to verify with an automated tool whether a program has a data race or not, because if it has one, it will definitely show up in a sequentially consistent execution. Alright, so now it is time to summarize what all we have learned. So what we have learned is that data race freedom is good because it helps us capture the intent of the programmer insofar as conflicting accesses to the same variable are concerned. SC as such does not imply data race freedom, but the brilliant result is that data race freedom regardless of the memory model implies SC, which is great. It allows us to write one program and run it everywhere. I can take the contrapositive of this and say non-SC execution implies data races, right, which would just be the same thing. And the next theorem is that if an automated tool cannot construct an SC execution that has a data race, then it means that the program is data race free. Or alternatively, if the program has a data race, then you will definitely see a data race in an SC execution. So the moral of the story is that if there are no data races, you are good. You have essentially written a sequentially consistent program. But of course, you have added a lot of synchronizing instructions throughout the program, which will reduce your performance. So you should minimize them. But assuming that is done, the memory model doesn't matter. All right. So what should programming languages do? Programming languages also define a memory model. For example, C++11, C++17 do define a memory model. And they also define these synchronization primitives, and they tell the programmer how to write code which is data race free, right? So almost all modern languages, C++, Java and so on, have their memory models. These are software memory models where they tell the programmer what they need to do to pretty much write code which is free of data races. So they provide these atomic synchronization operations. And programmers are expected to use these primitives which the programming language provides, right, to write what are called properly synchronized programs. And properly synchronized programs are this is one method of implementing a data race free program. Here the idea is that whenever I access a shared variable or a critical section, I protect it with a lock. And then after executing the critical section, I unlock it. And of course, for the same variable, I always protect it with the same set of locks. Even if it is accessed by some other thread, it is never the case that two different locks are actually protecting the same variable. So one variable is always associated with one set of locks. That will ensure that I can access it only after acquiring those locks. So this ensures a strict synchronization edge. So if I write my code in such a way where all my shared variables are encapsulated in critical sections, in the manner that I described, the program is properly synchronized and consequently data race free. And this will further mean that all accesses to shared variables are protected, and there are no concurrent conflicting accesses, right? So in a certain sense, what we have done is that we have built a lot of theoretical foundations. This is primarily for the architecture. Furthermore, this is also for the OS writer and library writer who really care about low-level performance, and these people do not want to write code that has a lot of fences or synchronizing instructions, because after all, somebody needs to write the code for the locks, right? So if, let's say, we can omit a few synchronization instructions, the performance of our locks will improve substantially. So a lot of low-level programmers need to be aware of the memory model because they can't afford that many fences. But any high-level programmer should use the idea of data races to essentially write properly synchronized code, let's call it PS code, where all shared variables are wrapped within critical sections and there are no conflicting concurrent accesses, right? So that is how the code is structured. If that is the case, regardless of the underlying memory model, the code will work in a sequentially consistent manner everywhere, right? As long as it's data race free. But of course, the downside is that the performance will be low because we'll be adding a lot of these slow fence like instructions. So performance will reduce. So as opposed to these nice handcrafted libraries where we have few synchronizing instructions, because we also use the features of the underlying memory model to establish dependencies. So there is a trade-off over here between simplicity, programmability and efficiency. But we did build up Efficiency is more important for the low level programmers, but for high level programmers, they need not be bothered with the memory models. They just need to ensure properly synchronized parallel code. So we'll take the argument a bit further and look at an even simpler method of parallel programming. So simpler than, let's say, what we have seen up till now, which is critical sections, and also, this OpenMP code that we wrote, that does embody all of these all all the discussion regarding critical sections within OpenMP directives. So programmers typically don't get to see that. But of course, if multiple threads will access the same variable, they need to you do have a lock and unlock kind of mechanism. So we will now make it even simpler and introduce an even simpler programming model, which needless to say is data race free, and it substantially eases the burden on programmers and shifts a large part of the burden to either system software or hardware. We will call this transactional memory. That will be the topic of the next lecture.